Welcome to the Explainer. So today we're tackling a really fascinating real-world programming challenge. This comes straight from the notes of a developer named Ang, dated July 2026. Now, if you've ever wrestled with data formatting in software, you already know, doing it elegantly, it can be surprisingly tricky. Ang's notes give us this brilliant little window into a specific Haskell programming problem. How do we efficiently convert numeral digits into entirely different formats? And to solve it, we're going to use data structures called tuples, along with a really cool feature known as list comprehensions.
Okay, let's dive right into this, because the practical challenge here is something developers face all the time: localization and formatting. Imagine you're trying to take a standard Gregorian year, right? Like 2026. And you need to translate it into two completely distinct numeral systems. On one hand, you need your regular, simplified Chinese translation. Simple enough. But on the other hand, you also need the formal financial Chinese characters. These are significantly more complex, and they're designed specifically to prevent forgery in banking. So our mission today is figuring out how to build software that can handle both of these distinct outputs seamlessly.
Section 1. The numeral conversion problem.
When you're faced with needing to output two completely different sets of characters for the exact same input digits, the most obvious approach is usually the most literal one, right? You might just be tempted to write two totally separate blocks of code to handle each translation. But, as Ang points out in the notes, writing completely separate character maps is incredibly inefficient. Just imagine having to maintain two distinct dictionaries in your software. You find a bug in one, well, you've got to remember to fix it in the other. And we all know that special kind of midnight debugging pain that comes from forgetting to update duplicate code. Plus, if you ever want to add a third numerical format later on, you're basically building a whole new dictionary from scratch. It's tedious, it's redundant, and honestly, it's a perfect recipe for introducing bugs down the line.
Section 2. Building a unified map. So instead of scattering our translations across all these different functions and variables, Ang's elegant solution is to use a unified structure. We're essentially going to put all our eggs in one very well-organized basket, which we'll call a combined mapping table. To build this in Haskell, we rely on a fundamental data structure known as a tuple. Now, if you're familiar with databases, you can basically think of a tuple as acting like a single row of tightly related data. It just groups a fixed sequence of elements together. For our specific case, we need to group the input digit, the regular translation, and the formal translation, locking them together so they always travel as a pack within our code.
Now, what's really interesting about this is how perfectly the tuple solves our organizational problem. You see the Gregorian digit, the regular character, and the formal character all beautifully combined into a single three-element tuple. For the digit 0, both translations actually happen to be the exact same character. But for 1 and 2, you can clearly see the distinct regular and formal financial characters living side by side in perfect harmony.
And this pattern continues for all the digits. This snapshot of Ang's actual code, which is appropriately named Digit Chinese Map, shows every single translation neatly packaged together in one centralized place. It's clean, you know? It's easy to read and it's super easy to maintain. But it does introduce a brand new challenge.
Section 3. Dissecting list comprehensions. Think about it. If our data is now locked inside a three-element tuple, how in the world do we pull out just the pieces we need? When a user asks for the regular Chinese year, we definitely don't want to accidentally hand them the financial characters too. We need a way to surgically extract specific items from our unified map. Enter the list comprehension. This is an incredibly powerful, concise feature in Haskell. It's a programmatic tool specifically designed to generate a brand new list by filtering and transforming elements from an existing source list. It is quite literally the exact tool we need to parse through our digit Chinese map and reshape our three-element tuples into two-element tuples right on the fly.
To truly appreciate how Ang pulls this off, let's break down the anatomy of a list comprehension into three really clear, digestible steps. First up, you declare your output expression, basically what you want the final data to look like. Second, you have a dividing pipe symbol. And third, you declare your source list and any filters you want to apply. It reads almost like a mathematical equation, but it's purpose-built for data processing.
Actually, I want to pause on that middle step for just a second, because that pipe symbol, it's the absolute key to reading this syntax comfortably. When you look at Haskell code and you see that vertical bar inside the brackets, you can mentally translate it to the human words where or such that. It acts as a logical bridge between the result you want on the left and the rules to actually get it on the right.
Section 4. Extracting the right data. And this brilliantly illustrates how it all comes together.
Now that we have our unified map, let's look at the actual code Ang uses for the regular translation. Remember our list comprehension anatomy from a minute ago. On the left side of the pipe, we have our output expression, a two-element tuple featuring D for digit and R for regular. We are literally asking Haskell to give us a list of D and R where the source is our three-element map over on the right.
But notice the really clever trick happening on the right side of the equation. To get our output, we tell Haskell to look at the source tuple, mapping D to the first item, R to the second item, and then we use an underscore for the third item. That underscore acts as a placeholder. It tells the compiler, hey, I acknowledge there is a third piece of data here, the formal character, but I want you to completely ignore it.
Let's move to the next part and see how this builds when we switch to the formal financial numeral. Check out the code now. Our output expression on the left changes to request D and F, the digit and the formal character. And on the right, in our source rules, the position of that underscore has moved.
By simply shifting that underscore into the middle position, we're now telling the program to ignore the regular Chinese character. This perfectly isolates the Gregorian digit and the formal character, linking them together into a brand new two-element tuple that's completely ready to be used by the formal formatting function. Honestly, it is such a highly efficient way to slice the data.
So, what's the real-world result of all this elegant logic? Well, when we run the standard year-to-Chinese function on the input 2026, the code looks up the digits, uses the list comprehension to filter out the formal characters on the fly, and effortlessly yields the regular Chinese translation of the year.
And right in parallel, when we call the year-to-Chinese formal function, the exact same base map is used. But this time, the list comprehension drops the regular characters entirely, giving us the complex financial characters for 2026. That's two distinct outputs, flawlessly executed without ever needing to duplicate our core data dictionary.
So, the crucial point is that Ang elegantly eliminated data redundancy here by combining the translations into a single three-element tuple and using list comprehensions to extract only exactly what was needed. We ended up with two clean functions powered by a single, super easy-to-maintain map. And as Ang notes, future refactoring could actually reduce those two functions into just one, making the code even tighter.
It really makes you think about the architecture of the systems we build every day. I mean, if a single line of a Haskell list comprehension can completely reshape our data and eliminate an entire redundant dictionary, what other code redundancies are hiding in plain sight in your own work? Sometimes the most complex formatting problems just need a simple, unified perspective. Thanks for joining me on this explainer.